Discuss about the next lecture of this fin, uh, and the agenda of this lecture and this class. We will consider in this lecture the error measurement of temperature in thermometric well and some numerical problem of the fin here. And this is a very conceptual lecture because here we learn about the application of theory of fin for error measurement. So let us discuss about the error measurement. So actually this error measurement is required when we are considering a thermometric well. What is the thermometric well? Thermometric well is a tube which is radially welded in inward direction of pipe in which fluid like oil, steam, etc. are flowing. Now if you observe my cursor, see this is the this is the pipe, and in this pipe there is a tube, clear, and this tube is made of this tube is made of some metal, not a glass. It's made of a metal, and it is radially inward welded with the pipe. And in this one, if you go observe this one, there is a filled with some oil, which is a conductive oil, and there is a one thermometer is inserted for measuring the temperature, and the mouth of this well is well insulated. That means there is no particular heat transfer in that direction. So I am writing the things, the diagram of a cross section. Actually this is the cross sectional view of a pipe with thermometric well. So this thermometric well, the basic the diameter of this pipe is D, diameter of the pipe in which a fluid like a steam, oil, etc. are flowing, which has a uniform temperature TF. And in this one, a radially welded inward direction, this is the thermometric well. Observe my just see my this cursor, and it has internal dia is Di. This is the internal dia is Di. I am writing this D, but it is a Di, and the thickness of the wall of the tube is del. Clear? So if you observe in this particular why I am saying that this is the application of the fin, in this one, if you see this cross section, this is a wall in which a circular fin is attached, because this is the extended part. So if you observe the temperature distribution from x is equal to 0, that is this as the root of the pipe, to that end of this tube, definitely there is a temperature difference. This is a maximum temperature, which is a T naught, and when we are moving further from x is equal to 0 to the x is equal to L, where the L is the length of this thermometric well, so definitely TL has a very much less as compared to the T naught. And here this thermometer is inserted at this position, so it measures the temperature TL. So if you do the just apply the theory, this is the surrounding temperature. This TF is considered as the surrounding temperature. You just see my cursor. TF is a surrounding temperature. K is the conductivity. I am considering the conductivity of the thermometric well is K. Thickness is del. Internal diameter is Di. Outside temperature is TF. Temperature at the root of the base is T naught, and temperature at the tip of the fin is TL. Clear? And one more thing I will discuss for that. The thing is, if you observe the maximum area exposed for the surrounding fluid is these areas. आप मेरे cursor में देख रहे हैं, this cursor. So these area are exposed more for the fluid which is flowing in the pipe. But if you compare the area of exposed area, this is the curvature in nature is less, because this area is less as compared to the this vertical area, because the vertical area is more exposed to the surrounding fluid as compared to the tip of this thermometric well. So for analysis purpose, we are considered as rate this tip is insulated because the rate of heat transfer through the tip is very low as compared to the rate of heat transfer through the wall, these vertical walls, so that we are considered as the case of insulated tip for finite fin. So it's a case B. So if you apply the theory of case B in this one, so I'm just writing the temperature profile for case B. So at x is equal to L, the temperature is TL. So we can write theta L upon theta naught is equal to cos HM L minus x divided by cos HML. Clear? So at x is equal to L, this is TL. So it is a TL minus TF divided by T naught minus TF, which is equivalent to the cos hyperbolic M L minus L upon cos hyperbolic ML. So this cos hyperbolic M into 0 is written as 1 upon cos HML. So this is the TL minus TF divided by T naught minus TF is equal to 1 by cos HML. Now, what is this? TL is the temperature of the tip of that fin. Here the fin is a, this is a circular fin. Clear? This is the circular fin. It is not a rectangular fin. It's a circular fin. TF is the real temperature of the fluid. Clear? But definitely due to the thermometer and this extended surface, the temperature measured by thermometer is TL, which is not equivalent to TF. That's why the error comes. So what is the error in temperature? This is the TL minus TF. Clear? And T naught is the base temperature, L is the length of the thermometric well. Now if you are talking about in technical terms, what is the thermometric error? That error in temperature of fluid is TL minus TF. But if you write in a thermometric error, it is the ratio of TL minus TF to the maximum temperature difference. This is T naught minus TF, or say the measured temperature. This is a T naught minus TF because this is a root temperature to the fluid temperature. And one more thing, here we are considering only conduction rate of heat transfer and convection rate of heat transfer. The radiation rate of heat transfer is negligible for the case. Clear? So this is the thermometric error, TL minus TF upon T naught minus TF is equal to 1 by cos HML. So definitely what we are trying to do for designing a thermometric well as the thermometric error as low as possible. So for this the cos HML value plays a very important role. If cos HML value is low, definitely thermometric error is high. If cos HML value, I am just writing the thing. If cos HML value, this one, see, if cos HML value is high, what happened? The thermometric error, this is the thermometric error, this value is low. Clear? So definitely what is our objective? Our objective is to reduce the thermometric error by considering the higher value of cos HML. Clear? So how can you do this thing? By considering the higher ML value. Clear? Higher ML value as a cos hyperbolic high value. Clear? So how to consider the ML value? L L has some restriction and the restriction I will discuss further. So let us discuss about the value of M. So M is written as under root HP upon KACS, where the parameter. Now the question is how to write the parameter and all that. So for this, what is the parameter? Parameter is equal to the pi di plus 2 del. Definitely this thing is no issue because the internal dia is di, and if you talk about the external dia, definitely this is a di plus del, so it's a pi into 2 del. Here so it is written as pi d naught here. And one more expression, one more thing I will tell you for that. This is pi di plus 2 del, this is a pi d naught, where d naught is the external diameter of the tube. Now I am considering the case. The case is if del is negligible. Del is negligible in the sense of del value is as low as compared to the, if you are talk about the internal dia. So this is del is very much less than di. So we can write parameter is equal to pi into d naught or pi into di, because di and do is very much similar because del is not affected. Del is very less quantity as compared to the di value. Now if you want to talk about the area of cross section, most of we have issue with the area of cross section. So I will discuss by making some diagram for that. Now see, if you, this is the this one is, this is your YouTube. Clear? This is your YouTube. Sorry, this is your YouTube. Now if you open this, just open this like so it is converted like this. It's a converted like this. Clear? And the heat transfer is taking place in that direction. This is the rate of heat transfer. Clear? In that direction. This is the direction. So if you open this, it is converted into a simple plate, and here the rate of heat transfer in that direction. This is Q convection, yeah, Q conduction, whatever it may be. Clear? This is the rate of heat transfer. So this distance, what is this distance? This distance is del. Clear? And what is this distance? This particular distance is the perimeter. Clear? This is the perimeter. Definitely this particular this is a di. Clear? I am writing this is the pi into di. This is the perimeter अगर मैं inside बात कर रहा हूँ, and outside if we are talk about, this perimeter is equal to the pi, sorry, this is pi into d naught. Clear? So if you are considering the area of cross section, because this is the area of cross section, so area of cross section, the area of cross section we can write like the perimeter, this particular length, which is a perimeter, and this perimeter is multiplied by del. Clear? This particular length is multiplied by del, so you can say this is the area of cross section, which I am writing over there. So this is p into del. Clear? And what is the perimeter? Perimeter is equal to, this is pi d naught कह सकते हैं, the pi d naught, but if you are considering del is very much less than di, so perimeter is written as pi di, because del is considered as negligible. So this is pi di. So we can write pi di into del, because del is very much less compared to the di. Clear? So this is the area of cross section. So it is very important to understand about the area of cross section and the perimeter in case of this tubular fin. Clear? So now move further. Now if you move further, so if you move further, and if di and do are given in the problem, so there is definitely area of cross section pi by 4 d naught square minus di square. That means del is not negligible quantity. But if you are considering del is a negligible quantity, so you can write the m is equal to, this is the m is equal to under root hp upon cs. So you just put the perimeter value, this is the pi into di, and area of cross section is pi di into del. I am purposefully converting this m in some specific terms, by which you can alter the value of ml. So it is m, so this m comes, I'm just again taking the notation. So this m comes with, now this m comes with, see, this m comes with, this is under root h upon k into del. Clear? So this, why? Because this pi and pi will be cancelled out, this di and di will be cancelled out, so this is the h upon k del. So definitely for higher value of m, what we are considering, the h value is high. Clear? H value should be as high as possible. Clear? H value as much as possible. And conductivity should be as low as possible. This is the conductivity. Clear? This is the conductivity, which is as low as much possible. And definitely this one is a designing factor. The thickness of the well is also very much less. Clear? The thickness is also very much less, so that m value is high. And definitely if you are talk about the ml value, if you are talk about the ml value, so if m is high, definitely L is high. So if you are considering the length of the thermometer is high, so the cos HML value, if you are considering ml value is high, definitely cos, that is cos hyperbolic ml, cos hyperbolic ml, if cos hyperbolic ml is high, why? Because ml value is high, so cos hyperbolic ml value is high. So what happened? The thermometric error is low. Clear? So for this m value is high by considering higher convective heat transfer coefficient of flowing fluid. Second one is if the conductivity of the thermometric well is low as much as possible, and the thickness of this thermometric well as low as possible. Clear? So if you are considering these type of designing factor, so you can say the thermometric error as low as possible. Is that clear? Now one more important thing in that one is that that I'm just expressing this thing, that is the two terms, that is the difference between the thermometric error and the error in temperature measurement are described as follows. Thermometric error, I already told you that this is the ratio of TL minus TF upon T naught minus TF, but error in temperature measurement is TL minus TF. Clear? So it is a very important thing. What is the error in temperature measurement? This is TL minus TF. What is the thermometric error? TL minus TF upon T naught minus TF. So easily you can understand this thing. Now let us discuss about the numericals of the fin. Let us take the first numerical of this problem. If it is required to heat oil to about 300 degrees centigrade for frying purpose, a ladle is used in the frying. The section of handle is 5 mm into 18 mm. This is a rectangular area of cross section. That means it's a rectangular thing. The surrounding air at 30 degrees centigrade, the conductivity of the material is 205 watt per meter degree centigrade. If the temperature at a distance of 380 mm from the oil should not reach 40 degrees centigrade, determine the convection heat transfer coefficient. Okay, so for this purpose, let us take, for this purpose I am just considering the important data for that. So in this case, the area of cross section of ladle is given. This is 5 into 18 mm. The ambient air temperature, which is a 30 degrees centigrade. Conductivity, this one is 205 watt per meter degree centigrade, and the distance, the temperature 40 degrees centigrade at 380 mm distance, which is mentioned in given data, and ambient air, the base temperature. Why I am considering this one as a base temperature? See, this is the some pot in which there is a oil. Clear? This is the oil. This is the oil, and there is a ladle. Clear? Ladle, some shape like this. This is the shape of ladle. Clear? Where the area of cross section is rectangular in shape. Clear? So here the temperature is 300. This is 300 degree centigrade. So this is the temperature here, the 300 degree centigrade. So this particular space is considered as the wall. Clear? This is considered as the wall. That's why this is the T naught temperature. Clear? Now now the question is, it is for fin cases. In most of the problem, it is not mentioning that the type of case. Either you are considered the infinitely long fin, either you are considering the finite fin of tip is insulated, or heat transfer at tip by the convection. Clear? So it is not mentioning in that in most of the problems. So how can you judge this? It's a infinitely large fin or a finite large fin. So this thing is use your presence of mind by considering the area of cross section and the length of the fin. Here length of the fin is not given in the problem, but the thing is given. If you observe this 5 mm and 18 mm, but there is some distance at which this is a 380 mm. So as 380 mm and 18 mm, if you compare those quantities, so 380 mm is very much high as compared to the 18 mm value. So you can say it's an infinitely large ladder. But if you are going to solve this problem by finite fin, there is no issue. But the thing is, the important thing is, always you just write in the solution what the assumption you are following for solving that the question. Here I am assuming this is the infinitely large ladder. I am considering it's an infinitely large type of fin. Why I am considering fin? Because this is the extended surface for that wall, so it is considered as a fin. So it's an infinitely large ladder. So we are using this concept theta x upon theta naught is equal to e to the power minus mx. So simply this is a tx minus ta upon t naught minus ta, which is equal to e to the power minus mx. Now tx value is given in the problem. Each and everything is given. Only m is unknown. Why m is unknown? Because you know the value of m is equal to under root hp upon kcs, where h is unknown for you. So you are not able to evaluate m. So by this expression you easily evaluate the m value, which comes 8.673. So once you have the m value, you just put over there, and only h is unknown for you. So you just consider the h value, evaluate. So it's h is unknown for you. So you just evaluate the h value. Parameter, this is 2b plus y. Clear? So definitely which one is b and which one is y, it is important again. So if you observe this particular, this is considered as y, and this is the 18 is considered as the width. This is the b. Clear? So this is the thickness and this one is the width of the fin. Okay. So this is the one of the problem. Let us discuss about some another problem. Let us discuss about some another problem. Okay, so let us discuss about the second problem. The second problem is there is a motor body which has a 360 mm in diameter and 240 mm long. Its surface temperature should not exceed 55 degrees centigrade when dissipating 340 watt longitudinal fin of 15 mm thickness and 40 mm height are proposed. The convective heat transfer coefficient is 40 watt per meter square degree centigrade. Determine the number of fin required. Atmospheric temperature is 30 degrees centigrade and thermal conductivity is 40 watt per meter degree centigrade. So for that purpose, I am just expressing the diagram. In this diagram, if you observe, this particular area is the this is the some machine. This is a motor body which is in a rectangular shape. Why I am considering rectangular shape? Because the 360 mm in diameter is given, which is the 360 mm. This distance is the 360 mm. In which the rectangular fin. Why I am considering the rectangular fin? Because why I am considering the rectangular fin? Because this is the 15 mm thickness and 40 mm height. So definitely the thickness and height is given. So it is not a circular fin. It must be a rectangular fin. But if you closely observe, why I am considering this problem for considering the length, width and thickness. So accordingly, in this one the fins are longitudinal. So according to length, it is look like this. This is a rectangular fin. In this one, the yellow color distance is considered as the height of the fin. The red color distance is considered as the thickness of the fin, and this is considered as the width of the fin. Clear? So the length of the motor is considered as the width of the fin, because rate of heat transfer in that direction. See just my cursor, heat of transfer in that direction. So if the heat of transfer in that direction, so it is a longitudinal direction. So this one is considered as the length of the fin, and it is a transverse direction. So it is a width of the fin, and definitely it is the thickness of the fin. So now you just note down the data, which is again I am writing this diameter, which is misleading for this data is given only for the misleading you. This 240 mm long is the width of the fin. Already mentioned, this is the width of the fin, and I expressed by the diagram also. T naught is the base temperature. Why T naught is the base temperature? Because it is written as its surface temperature should not exceed 55 degrees centigrade when dissipating 340 watt. Total heat transfer by the motor is 340 watt. So the surface temperature is not more than 55 degrees centigrade. So this is the maximum possible temperature of surface. So you can consider the T naught is 55 degrees centigrade. Now the rate of heat transfer, actually this is the rate of heat transfer. So it is Q, total rate of heat transfer. This is a 340 watt. Convective heat transfer is 40 watt per meter degree centigrade, and thermal conductivity is 40 watt per meter degree centigrade, and convective heat transfer is 40 watt per meter square degree centigrade. Both values are given. And the length of the fin. See, length of the fin, I am considering the height of the fin. Why? I already told you, this is the, this one is motor body, and definitely this is the fin is attached over there. This is the fin is attached over there. Clear? This one is the fin is attached over there. So this is the height. Clear? This one is considered as the height. So this height is the basically the length of the fin, and definitely this one is considered as the width of the fin. This is the width of the fin, and this one is considered as, this particular distance is considered as the thickness of the fin. Why? Clear? इसको आप ऐसे भी देख सकते हैं. Now if you observe, if you just take in vertical condition, the each and everything is clear to you. This is the fin. This is the fin. This one is the fin for you. Diagram is very much not clear exactly. So this is the length of the fin, because height is considered as the length of the fin. So length of the fin is 0.04 meter. Now the ambient air temperature is given in that one is 30 degrees centigrade, and the thickness is given as 15 mm. So conductivity is this one. So now the thing is, each and everything is given. So the first step for fin problem is always evaluate if the all the things are given. So always evaluate the m value, because without m value you cannot move further. So you just consider the m value. Now the second important thing which I told you in that one, if you are considering a infinite long fin, there is no issue. But if you are consider a finite fin, so always you consider the case C, that means heat transfer active by convection, until or unless the specific situation is given in the problem, that is tip is insulated. If this thing is written in the problem, tip is insulated, there is no issue, you consider the case 2. Otherwise, always for the finite fin, consider the case C. Clear? Definitely in a case C, there is a very this is a very long expression for temperature profile and rate of heat transfer. So you just consider the second approach, and the second approach is evaluated by this considering the characteristic length, which is the L plus AC by P. This AC by P is already, this is the LC. So AC by P, area of cross section divided by perimeter. So area of cross section you already calculate by B into Y, and perimeter is 2B plus Y. You just put all those values. So you get the characteristic length value LC. Now if you calculate the rate of heat transfer by one fin, so this is the under root HP KCS theta naught tan HMLC. So this comes 21.76 by putting all those values. Now here the total rate of heat transfer is 340 watt. The 340 watt is the total rate of heat transfer, and heat transfer by one fin is 21.76. So how many fins are required to transfer 340 watt? So you just divide this one, so it comes 15.62, which is approximately, for complete number, it is 16 fins. Clear? Now let us move for next problem for this lecture. So let us move for next problem. So let us talk about the problem number 3, in which a steel rod, conductivity 30 watt 32 watt per meter degree centigrade, and 12 mm in diameter and 60 mm long, with an insulated end, is to be used as a spine. Why I am considering this problem? In this problem it is mentioning that that is diameter, that means it's not a rectangular fin, it's a circular fin, and area of cross section from root to the tip is uniform. So you can apply the same theory as you learn in the fin classes. Clear? If the area of cross section from the root of the fin to the end of the fin or tip of the fin is uniform, you can use the same theory. So this is the diameter of the fin, and the length of the fin is already given. So what are the given data? This is the conductivity. So conductivity is given, that is 50, where it is written, the conductivity is given, this is the conductivity is given, and the diameter is given 60 watt. Length of the fin is given, that is 12 mm in diameter and 60 mm is the length, both things are given, and the ambient condition is 60 degrees centigrade. Heat transfer, convective heat transfer coefficient is 55 watt per meter degree centigrade, and the base temperature is 90. Now the perimeter is pi d. You easily calculate area of cross section pi d square by 4. So first step is to evaluate the m. So under root hp upon kcs, this is m value is 23.91. Now if you observe this problem, it is clearly mentioned that it is with an insulated end. That means it's a finite problem, finite fin problem with insulated tip. So you use the insulated tip concept. So first part is the evaluate the fin efficiency. So it's a Q actual upon Q maximum is evaluated by the application under root hp kcs theta naught tan HML over HPL theta naught. So just put all those values. You easily evaluate the efficiency, which comes 62.2%. So now next problem is for this. Next is the temperature at the half of the spine. So this temperature profile theta x upon theta naught is equal to TL by 2 minus TA upon T naught. Why TL by 2? Because we need to calculate the temperature at the mid of the fin. So x is equal to L by 2. So you just put x is equal to L by 2. So this is the cos HM L minus L by 2 divided by cos HML. So it comes cos HM L by 2 upon cos HML. So this is that TL by 2. So each and everything is given in that problem. So you easily put all those values. That means if you put the value, see this is the TL by 2. ML value you already calculate in earlier slide. So you just put the M value, L value, and all those values. You get the temperature at the half of the fin is 80.01. Now the last problem for last section of that problem is to evaluate the rate of heat transfer from the base. So Q fin is equal to under root HPKCS theta naught tan HML, because it's a case of insulated tip. So you just put all those values, you get the 2.7 watt rate of heat transfer. Now one thing is important for one thing is important for that. One thing is important. Here it is only written the heat dissipation. So how can you say the heat dissipation from the root? Yes, of course, it's a very important thing. Always when it is written the heat dissipation or heat transfer from the fin, so definitely it meaning that the heat transfer from the root. Clear? If it is mentioning that find out the heat dissipation at the half of the fin, so definitely you calculate the del T over del X at x is equal to L by 2 and put all those values and just derivate some formula and put in that formula and evaluate the rate of heat transfer. But if it is only mentioned that find out the rate of heat transfer, that means it's already it's meaning that calculate the rate of heat transfer from the root of the base. Okay. So let us move for next problem. This problem is this is the problem in which we are. Let us read this first problem. A thermometer pocket 2.2 centimeter in diameter, 0.5 mm thick, is made of steel. Conductivity is 27 watt per meter Kelvin, and it is used to measure the temperature of the steam flowing through a pipe. Calculate the minimum length of the pocket so that the error is less than 0.5% of applied temperature difference. Take steam at 250 and convective heat transfer is equal to 98 watt per meter Kelvin. Okay, so now let us discuss about this problem. You just see my cursor. Now in this one, this is the thermometer pocket, 2.2 centimeter in diameter. So this is the diameter and 0.5 mm thick. So definitely this is the internal dia. Clear? This is the DI, and this is the del. Conductivity is given. This is 27 watt per meter Kelvin, and the error. See, read again. So that the error is less than 0.5% of applied temperature difference. Now, what is the applied temperature difference? Applied temperature difference is nothing. This is the T naught minus this is TF. Clear? This is the applied temperature difference. So here the error, what is the error? अगर मैं error की बात करूंगा, so error is, this is the T, this is the error which is the TL minus this is TF. This is the error. Clear? So TL minus TF is equal to the 0.5% of T naught minus TF. This is given in that problem, and the TF is, this is 250 degrees centigrade, and convective heat transfer coefficient is 98 watt per meter Kelvin. So you just apply the theory of thermometric well error temperature measurement. So first of all, you evaluate the M value. So M value is equal to under root HP KCS, where perimeter is equal to in this one, and area of cross section is this one. Now here the question is, why I am not neglecting the 2 del in that expression? Yes, it's an important thing. If del value is given in that problem, keep in your mind, and it's a very important, if del value is given in that problem, so definitely for easy calculation or say without any assumption calculation, definitely you consider the del value. If you are neglecting the del value, either it is given in that problem, so first of all you just write the assumption. Clear? If you not writing assumption and you consider del as negligible, definitely your answer is wrong. So if you want to neglect the del as compared to the diameter, internal diameter of the thermometric well, definitely you write the assumption, otherwise you consider it. So I am suggesting you always you consider it. So you just consider this del value, so M value comes 85.2. Now what is the concept? This is the theta upon, this is theta naught, this is theta naught, this is actually theta L. This must be equal to 1 by cos HML. Clear? This is equal to 1 by cos HML. So this theta L is equal to written as, this is TL minus TF upon T naught minus TF is equal to 1 upon cos HML. So definitely if you just write this thing, this is the TL minus this is TF is equal to what it is, this is 0.5 0.5% of this T naught, this is T naught minus this is TF. Clear? This is T naught minus TF. So I am writing this is TL minus TF upon T naught minus TF is equal to 0.5 divided by 100, and this comes 1 by cos HML. So by this expression you easily evaluate the ML value, and you already have the M value, this is the 85.2, so you can get the L value, which is a 70.3 mm. Now the question is 70.3 mm is given in that one. Okay, so it's a minimum length of the pocket, so that error can be minimized by 0.5%. Now the thing is, if suppose it is given also that this is the pipe, and this is the your thermometric well, and if this length, this is the length, this one is the length, this is the length of thermometric well, and this is the diameter of the pipe. Clear? Where the fluid is flowing. Is it possible that L is greater than diameter? Yes, of course it is possible. How? By considering the diagonal. Clear? Like this. If you are considering this is the pipe and L is higher, L is greater than the diameter of the pipe, so you can consider the thermometric well like this. Clear? You can consider the thermometric well like this. So we are considering the length of the fin is like this. Clear? So in that case we are considering the L is greater than the diameter. Clear? So if suppose the diameter of the tube is given in that problem, say for example it is given that it's a 60.3. If suppose it is given in that problem, the diameter of the pipe is 60 mm. Clear? And here the thermometric length is 70.3. So it is not meaning that your solution is wrong. You can say the length of the thermometric length is greater than the diameter of the pipe, so that we can adjust this thermometric well in diagonally like this, and make some diagram also. Clear? Okay, so I think for thermometric well and concept of fin, I consider most of the problem. So your doubt is clear for that, and for assessment we will provide one assignment also. Okay, thank you so much for this lecture, and definitely we will meet in next lecture. Thank you so much.